So welcome you back. So let us continue with our problem solving session today also. So last time we solved a few problems on general statistical inference problems, especially we did some problems or some applications of the results dealing with non-randomized estimators based on sufficient statistics. So especially if your loss function is convex, you can always find estimators which are non-randomized and are as good as any given estimator. So it's enough to consider only non-randomized estimators. So we did some problems in that context. Today let us try to do some problems on invariance. So we did a problem dealing with normal distribution last time. Let us do a couple of more problems today. So let us look at this problem. So what you have is x1, x2, xn is a random sample with PDF. So when I say with PDF, that means the common PDF of x1, x2, xn is f theta x, which is square root 2 by pi e to power minus half x minus theta whole square, x greater than or equal to theta, 0. Otherwise, where theta belongs to capital theta, which is whole parametric space R, find the MRIE under additive group of transformations under square error loss function. So let us try to see. So first I have to see that my probability model belongs to a location family. So let us try to see what is my joint density of x is nothing but let me call this as g theta, because f I am using over here, so let me write down this as g theta of x1, x2, xn, which is nothing but product I is equal to 1 to n root 2 pi root 2 by pi e to power minus half xi minus theta whole square. X belongs to Rn. This certainly can be written as f of x1 minus theta xn minus theta, where my f of t1, t2, tn is nothing but, in place of xi minus theta, I just put t. So 2 pi, 2 by pi to power n by 2 e to power minus half summation I is equal to 1 to n ti square, t belonging to Rn. So this is certainly a location family. So my problem is invariant under the additive group. I know what are my group of transformations G bar and what is the induced group of transformation on the Xn space. So under such a situation, I know what MRIE is. So first, let us try to see if I can find a complete sufficient statistic over here. Now if I apply the factorization theorem over here, theta would come with summation xi, and actually this is when each xi is greater than theta. So this would be if minimum is greater than or equal to theta, right? So x1 is greater than or equal to theta. This x1 is basically minimum of. So you can see when I apply the factorization theorem, theta would come with summation xi, x1 would come with theta. So the minimal sufficient statistic is x1 and x bar. Note that here only I have one parameter, one dimensional parameter, statistics are 2, so this is not going to be complete. One can see it is not complete. So that Basu's theorem kind of a technique will not work over here, because MRI would be then, so I can take delta naught x to be x bar, then MRI, I cannot say that that u star would be independent of d over here, because x bar and they may not be, x bar and di's may not be independent. So MRI is delta star x, which is x bar minus u star of d1, d2, dn minus 1. Now you know what are d1, d2, dn minus 1. Di is nothing but xi minus xn. So this is this, and your loss function is square error. So what you know is for any d belonging to Rn minus 1, u star d minimizes psi of c, which is expected value at theta is equal to 0 of w of all this. So w of, so which is x bar minus c whole square given d is equal to d. This is what this would be. Now the only issue over here is if this conditional distribution was independent of d, then my minimizing c would have been expected value of x bar at theta is equal to 0, which is easy to find from here, which is same as expected value of this probability density function under theta is equal to 0. But here, although it is ancillary, but my x bar is not a function of a complete sufficient statistic. It is a function of a minimal sufficient statistic, but not a function of a complete sufficient statistic. So I cannot conclude that x bar and d are independent. So I see a problem over here. So the only way I can get rid of this problem is I find the conditional distribution of x bar and d. But from the theory we know that in the case of square error loss function, we have an alternate formula for the MRI. And what is that? MRI under square error loss function is same as delta star x minus infinity to infinity t times f of x1 minus t xn minus t dt divided by minus infinity to infinity f of x1 minus t xn minus t dt, where my f is this. My f is this quantity. So this again over here, this would be if each ti is greater than or equal to 0, so what would be this? This quantity can be given by this expression provided each xi minus t is greater than or equal to 0, right? Each xi minus t is greater than or equal to 0 for I is equal to 1 to n. That means t is less than or equal to xi for each I is equal to 1 to n. T is less than or equal to each xi, that means t is less than or equal to minimum. So that means this density would be positive only when t is less than minimum, because each of these arguments have to be greater than or equal to 0. So xi minus t have to be greater than or equal to 0, which is equal to saying that t is less than or equal to x1. So with this, I can write down this as, let me use the other side of the board. So this is same as minus infinity to x1 t times f of x1 minus t and so on. So that is same as 2 by pi to power n by 2 e to power minus half summation I is equal to 1 to n xi minus t whole square dt divided by minus infinity to infinity 2 by pi to power n by 2 e to power minus half summation I is equal to 1 to n xi minus t whole square dt. I can simplify this. This becomes minus infinity to infinity t times e to power minus summation xi square by 2 e to power minus summation xi square by 2 would get cancelled both the sides. You will get e to power minus half n t square, then minus 2t summation xi, which is same as minus 2nt x bar dt divided by minus infinity to infinity e to power minus half. Again, summation xi square by 2, summation xi square by 2 gets cancelled. This becomes nt square minus twice nt x bar dt. I'm trying to make it a perfect square, so this becomes minus infinity to infinity t e to power minus n by 2 t square minus twice t x bar. Now what I can do is I can add x bar square over here. I can do the same thing in the denominator so that the effect nullifies. So this is same as e to power minus half minus n by 2 t square minus twice t x bar plus x bar square. This is to make perfect square because they will get cancelled out from numerator and denominator because they do not depend on t. Okay, so far so good. So let us try to make it a perfect square. So this becomes minus infinity to infinity t times, I can make it root n root 2 pi also, numerator and denominator, because root n root 2 pi can go in the numerator as well. Same as everywhere it should be x1, right? Because the density is positive only when it is x1. So minus infinity to x1, and then it becomes phi of root n t minus x bar. Root n by root 2 pi phi of root n t minus x bar dt. You can make the transformation root n t minus x bar is equal to z, something would come. You can finally solve this. Let me not give a final expression. You can do it in just 2 steps. Let me just give the final expression. This is going to be x bar minus 1 upon root n phi of root n x1 minus x bar divided by capital phi, which is a distribution function of a standard normal, root n. So to do this, let me just give you a hint. I make the transformation root n t minus x bar is equal to z. Right? Range becomes root n x1 minus x bar, and that is how this root n x1 minus x bar is coming. Then some distribution function will come, and then phi z. So you'll get numerator integral of the type minus infinity to infinity z phi z dz. Now note that this is same as minus infinity to infinity. Z phi z can always be written as d by dz of minus phi z. So it would be minus infinity to root n x1 minus x bar. So if that is the case, it becomes, integral becomes as this. So this would become phi of root n x1 minus x bar. And that is how this quantity is coming. And then one x bar will come, and they will get cancelled with the numerator thing. So this is what you will get. So let me do one more problem. So this was a problem where I am not able to use the Basu's theorem. So I am not able to get a complete sufficient statistic which is independent of D. And that is why if you look at that x bar minus u star D, so u star D is no longer a constant. It is depending on di's. Of course, one can get many other examples where such a thing happens. So let us do one example. x1, x2, xn IID with PDF, common PDF as f theta x as 1 by sigma naught e power minus x minus theta by sigma naught if x is greater than or equal to theta, 0 otherwise. Theta belongs to capital theta, which is r. Sigma naught is a known quantity. My loss function, which I take, is indicator function of t to infinity mod of theta minus a. What it means is this is 1 if theta minus a is greater than or equal to t, and 0 if mod of theta minus a is less than t. So which makes sense. It says that if difference between my xn and the true theta is smaller than the threshold t, which is given to you, then my loss is 0. Only when my xn is far away from theta beyond the threshold t, my loss is 1. So here loss is either 0 or 1. So find MRIE under additive group. Now in this case things are simple because one parameter, so x1 is complete sufficient. So one can easily see that this belongs to location family. So my x has the vector x1, x2, xn has a PDF g theta x, which is f of x1 minus theta, because that is what I have to see. It is of the type f of x1 minus theta, xn minus theta. X belongs to Rn. So, and theta belongs to capital theta. So where my f of t1, t2, tn from here, what is happening? F of T1, T2, Tn is nothing but 1 by sigma naught e to power minus summation I is equal to 1 to n Ti by sigma. So xi minus theta greater than or equal to 0 because T1 is taking a role of xi minus theta. So Ti is greater than or equal to 0, 0 otherwise. So it is a location family. So I know my estimation problem is invariant under group of transformations, additive group of transformations. So I can find the MRI. So first thing I do is whether I can make use of Basu's theorem, which I am able to do because it is a one parameter family, and I know that in this case the minimum order statistics is the complete sufficient statistic. So delta naught x I take as x1. This is belongs to di. Why? Because delta naught of x1 plus c, x2 plus c, xn plus c would be nothing but minimum of x1 plus c, x2 plus c, and xn plus c. So if you have to see delta naught of x1 plus c, xn plus c, that is nothing but minimum of x1 plus c, xn plus c. So which is same as saying that I first take the minimum, because c is common to all of them. So first I take the minimum of x1, x2, xn and add c to that. So this is same as minimum of but minimum of x1, x2, xn is same as delta naught x. So it is certainly invariant. This is also complete sufficient from your last course. And d is ancillary. So that means x1 and d would be independent, so that u star d will not depend on u. So MRI is delta star x, which is x1 minus u star, where u star minimizes psi c, which is expected value of theta is equal to 0 of w of x1 minus c. Now you can see my Wt is 1 if mod of W of x is 1 if mod of x is greater than or equal to t, 0 otherwise. So this will be same as probability that theta is equal to 0 mod of x1 minus c is greater than or equal to t. Now note that in this loss function t is a fixed quantity which is given to you. There is a threshold which tells you when below which the loss is 0 and above which the loss is 1. So I have to find the c which minimizes this. So I just need to know what is the distribution of x1 under theta is equal to 0. Now this is exponential. So from last course you know that n times x1 minus theta by sigma naught is exponential 1. So under theta is equal to 0, if I define z, which is n times x1 by sigma naught, this is exponential 1. That means its PDF is e to power minus z if z is positive. So I write down that psi c is same as probability that x1 is less than or equal to c minus t plus probability that x1 is greater than or equal to c plus t. So everything I can write down in terms of z, so that I am dealing with exponential. So this is saying that probability of theta is equal to 0. x1 is nothing but, so I can write down n by sigma naught, I can, sorry, this should be less than or equal to. So z is less than or equal to n by sigma naught c minus t plus probability that theta is equal to 0, z is greater than or equal to n by sigma naught c plus t. Let us first try to see this. This is exponential. What is the distribution function of exponential of z? It is 1 minus e to power minus z if z is greater than 0. For z less than 0, this is 0. So that means if this quantity is less than 0, then this is 0. So that means for c less than t, this is 0. What would be for c greater than or equal to t? This would be nothing but 1 minus e to power minus n by sigma naught c minus t. All right? Plus, what would be this quantity? Now note that if this quantity was less than 0, then this probability is 1, because z is always positive random variable. So that means if c is less than minus t, now note that t is positive, right? T is given to be positive. If c is less than minus t, then this is 1. If c is greater than or equal to minus t, it is nothing but e to power minus n by sigma naught probability z greater than or equal to c plus t, right? Because probability z greater than or equal to x is same as e to power minus z provided z is positive. Good, very nice. So I'm almost nearing the solution. So what does this become? So this has various branches. So one branch is c less than minus t. C less than minus t, this is 1. C greater than or equal to minus t and less than t. That means this and this. So e to power minus n by sigma naught c plus t. And what is for, sorry, this is c. What is for c greater than or equal to t? C greater than or equal to t, both the sides. So this is e to power minus, both get added. So 1 minus e to power minus n by sigma naught c minus t plus e to power minus n by sigma naught c plus t. So this is a function. I have to find the minimizing c. Let us see what is the behavior. So you have a 0 over here, let us say minus t over here and t over here. For c less than minus t, it is a constant function. For c between minus t to t, it is e to power minus n by sigma naught t, which is a decreasing function of t. So you get like this. Then what happens? For c greater than or equal to t, this is 1 minus, so these are increasing, this becomes a decreasing function of t. And then again you have a decreasing function of t, right? So this is coming out to be decreasing everywhere. So 1 minus e to power minus n by, oh, there is a plus sign over here. So this would turn out to be increasing function of t. So after that, this would be like this. So that means the minimum is attained at u star is equal to t. So u star, that means is same as t. So the MRI is so this clearly is decreasing, this is constant. And if you want, you can take the, I'll just show that why it is an increasing function, so that MRI is delta star x which is x1 minus t. So you can take the derivative both the sides. It becomes, if you take the derivative of this, and then you can just see that it is always greater than or equal to 0. So we could get the MRE. Let me do one more tricky problem, and then I can leave the rest of the problems to you, at least for the location invariant estimation. So this just is an increasing function. You can take the derivative and show that it is greater than or equal to 0. Now let us consider